All right, I guess we are starting. When somebody wants to ask a question, you can use chat to do it. And let me first introduce Professor Igor Sokolov, who is actually pretty much known at the AFM field. And but anyhow, Dr. Sokolov, AFM adventure started in 1987 in the Soviet Union when he encountered the first AFM made. Being trained as a quantum field theory physicist, his early AFM works were related to the search of unknown fundamental forces in the nature. Using AFM force measurements, he obtained the much stronger restrictions on the existence of new elementary particles that was previously found from the observation of red giant stars. He was awarded later by Jinxton International Fellowship Award from Stanford University for proposing ideas of lifting and tapping mode. These days, his interests gradually migrated to biophysics and medical applications of AFM. Presently, he is a professor of Tufts University with more than 170 referred papers, including publications in the elite journals like Nature, Nature Nanotechnology, PRL, Advanced Materials, Materials Today, etc. He has 21 patents issued and pending, including 6 in the area of AFM, related to medical applications of AFM, machine learning, ringing mode, and FT-nanoDMA mode. His current AFM-related interests are AFM for health, and his goal is to introduce AFM to the medical area. And now we would like to switch, the screen and to Professor Sokolov, and we'll ask him to start the presentation. Igor?
Oh, thank you. Do you see my screen?
Yeah. So.
Okay. So this presentation about 2 relatively new modes called ringing and FT-nanoDMA. Why it's called this way, I'll tell you later. So, but the idea is to create these modes as something which can produce a relatively large amount of information per second. Because force microscopy is known for its, one of the caveats of force microscopy is slow speed. And it can be compensated to some extent with the amount of information per second this microscopy can produce. So just like a couple of words for what I'm doing. So my interest right now is in physics of cancer and aging, plus development of new methods for imaging and data analysis, and new materials. So specifically, today I will speak about this part, new methods in imaging. So the outline of the talk is as follows. So there is first, why we need new modes at all. Second, what is ringing mode? What is FT-nanoDMA mode? What are possible applications at the end? Questions and answers. So the need for new modes. AFM has a serious problem of repeatability. That was almost the bottleneck for broad application of this technique for well, already a couple of decades at least. So for example, classical tapping mode is almost impossible to make quantitatively repeatable. There are, if I'm not mistaken, maybe like 100 of works trying to quantify phase imaging, but it's so sensitive to everything in the world, so it is not, hasn't been done as yet. AFM is relatively slow, so that's, well, that's a fact. Of course, you may know that there are so-called video rate AFMs. Those are kind of really narrow and mostly for high-resolution imaging of fast processes. And I would say that I still kind of have to see applications beyond some kind of just a few molecular images, which actually was really impressive, but just literally a few. AFM, but the most important part, I think, where AFM has troubles these days being broadly adopted, is simply mistakenly treated as an imaging technique. It's actually not imaging. It is like there are multiple imaging which are easier and better than AFM. But what is AFM is really unique is in mapping of physical properties of sample surface. And that's what these new modes are specifically aimed. So what is a ringing mode? So essentially it is a extension of a sub-resonance tapping, or one version of, there are multiple sub-resonance tapping, which originally was invented by BTEC, a German company, and now there are multiple incarnations of this technique. For example, there is peak force by Brucker. And we focus on the part which is typically ignored part of the signal. So this tapping, it goes like when probe goes up and down, touching the surface, developing some adhesion. On the way back, it actually produces some ringing. No matter what you do, unless you have really heavily damped cantilever, you have some ringing oscillations. Maybe not that many, but at least a few. And typically it's either filtered out, but at least ignored. And this is what we actually use, this part of the signal, to extract, surprisingly, quite a lot of different channels, new channels of information. So when you compare ringing mode to other modes, it makes sense to compare, for example, the contact, tapping, and peak force. Well, I would put QNAM because QNAM stands for quantitative nanomechanics. I'm not discussing how quantitative nanomechanics is, but it like at least gives you some number of information, which I listed here, like stiffness and deformation, which are quite unambiguous. So it's like up to 6 different channels. So contact gives you 3 channels: height, error, friction. Tapping, like height, amplitude of phase, or deflection of phase. So ringing mode gives you the same what subresonance tapping gives you, plus 8 more channels. So what is important also to mention about robustness. Robustness, it means at least repeatability. You can really repeat from one microscope to another. Like if you reduce number of channels to robust channels, for example, error signal is definitely not a robust channel. It literally depends on how big gains you use, feedback gains. So so it will reduce to 2, tapping mode really like maybe even 1, or total deflection maybe gives you 1 more channel. Subresonance gives you 3, like height, adhesion, and deformation. That's for sure, which is kind of independent. Stiffness maybe, but maybe not. But ringing gives you all 8, which are highly repeatable. So that's why it's really a data-intensive mode. So what it means, which modes? If I really go to one by one with deep explaining, so it probably will take another webinar, but just really mention a few. And description of all these channels in great details is presented in Nanoscience Solution website. It's very easy, like AFM-NSS. So I give you a few to have a flavor of what this mode can give you. First is restored adhesion. You'll see like why it's called restored. Well, we call it also averaged, but it's simply we'll see what it means. So regularly adhesion is just a really tiny moment at the force curve at which the probe no longer sustained by mechanical equilibrium contact with the surface and jumps up. This is really sharp event, sharp in time. So you really have to have super high digitalization to pick it up extremely accurately. Instead of that, we said, okay, but we better quantify the entire curve, and we know how decays. Actually, one of the fundamentals of this mode, why this mode even was created, when we saw that Q factor of all these ups and downs is a constant. So we really can apply damping harmonic oscillator model here. So we can literally extrapolate back in time the moment where adhesion happened. And it's not only measurement on one single point here, but we measure the entire curve. And using the formula, which is like fairly straightforward formula, describing sinusoidal oscillations and decay. So we can really use as many points, essentially, like as possible, as like needed, and to get very good signal-to-noise ratio. So that's why it's called restored, and maybe even averaged adhesion, because we have like quite a lot of different points. So this is an example of restored adhesion, and adhesion collected just a regular subresonance tapping at the same time. So by the way, that's an important part. All these channels that I listed can be measured at the same time. So it's literally like they all measure simultaneously. So just to give you a bigger view, this is restored adhesion, this is regular adhesion. So you can see the difference. Like for example, these spots are very nicely seen here and barely seen here. So resolution is better because of signal to noise now is much better. So to give you a feeling of the other two channels, which are really unique and really interesting channels, look at these simulations. So when probe touches the surface, it develops some neck, pull-off neck size. And that's what we can measure using analysis of those curves, force curves. We can even measure the amount, disconnection distance, size of the molecules, which can be stretched by the probe. And do it at each touch. Well, that's the sound like ding, that's why we call the ringing mode. When probe disconnects, it creates a ringing. So this is example of maps of pull-off neck height on a cell surface. And this is recording simultaneously peak force tapping, showing you the surface, the same surface of a cell. And you can see there are patches, and you can even measure size of these molecules. It's literally given you in nanometers. There are definitely patches on the membrane which are having different viscoelastic properties. Disconnection distance is size of the molecules attached to the surface. Again, this is a height for reference, height recorded with peak force tapping, and this is disconnection distance. So you can see it's also patchy, and the size of this can get up to probably like 300 nanometers. So it's definitely something interesting and never was reported before, to the best of my knowledge. So this is just to give you a flavor how multiple channels can be connected, even like if you have height and disconnection distance. This is red blood cell infected with malaria parasite. These bumps are where this parasite kind of tried to escape. And you see this, like if you put disconnection distance, which is size of the galactic helix molecules essentially attached to the cell membrane, you can see these bumps are bold. So there's no molecules attached to it, while the actual cell is covered with those molecules. This is just again like we still yet to understand this, and it's right now just in process of writing in the manuscript. Different heights. So you may get, because we record simultaneously position of the sample and deflection of the cantilever, so we can record the height of the sample at different forces. For example, at the moment of developing adhesion and disconnection height. Disconnection height is like when we have this projected disconnection distance or projected adhesion. So restored adhesion. And zero force height. Zero force, it means like height at zero force. And this is, for example, polystyrene, low density polyethylene blend, this classical sample for calibration of your mechanics, this provided by Brooker. And you can see like what happens with low density polyethylene. You can clearly see the difference between a regular height to its zero force height, pretty big adhesion height and quite large, even almost like noisy disconnection height. Disconnection is like the moment of last molecule was disconnected from the cell surface. Sorry, from the sample surface. So you can see it's like, first you can think it's like noise, but if you really look at like the pictures, you can see these are actually patchy. And at the same time, if you look at in the middle, it is polystyrene. It's pretty homogeneous, like all this, because it's pretty rigid and not a lot of deformation. Even not a lot of these dangling bonds, which we pull using the AFM probe. So this is just, again, like in 3D, you can look at some of the pictures showing you like adhesion height, where you pull off these material, low density polyethylene, zero force look like that, and the regular height look like, well, kind of a little bit iron out. So disconnection energy loss. This is another interesting thing, because regular disconnection energy, regular in, for example, peak force QNAM, is calculated as integral between approach and retraction curve. And our disconnection energy loss is literally energy or part of this area when the probe starts disconnecting from the surface. So it's literally from the moment of loss of equilibrium till the last moment of energy loss due to probably some either broken neck or some molecule stretched from the surface. So it is really tiny. So, and as a result, we actually have to also expect pretty high resolution, because at this moment, resolution is defined by the area of contact. And the area of contact is much, much smaller than at the full load force. So this is an example of dissipation, peak force QNM, and disconnection energy losses. And you can see that human cornea flake. You can more clearly see flakes, and surprisingly not really clear. There are less like these line artifacts. So this again are recorded simultaneously. So it actually means that these both channels give you slightly different information. So they sort of complementary. So it's pretty interesting. Mm-hmm. So phase shift. We call this dynamic creep phase shift. Essentially, it's really phase shift between oscillation of the sample and deflection of the cantilever. Regular subresonance stopping do not really measure those. But if we measure, we can really see surprisingly good, well, maybe a little bit noisy. We still speak about phase, not surprise. But for example, looking at, it's a very good phase contrast. Looking, for example, the small bumps in the surface of polystyrene and comparing to the phase, we can say that, hey, just these bumps are actually polystyrene, or at least look like polystyrene. So it's not low density polyethylene. So it's indeed, otherwise we'll see similar phase shift. So because phase is essentially viscoelastic losses, or just time-dependent losses. Mm-hmm. Advantages of ringing mode. First advantage is higher lateral resolution. Regular height, for example, is defined, a resolution is defined by literally area of contact. And the adhesion height, for example, is literally when you have last moment of disconnection. So it's really small compared to the full developed contact. And if you compare polyurethane surface, adhesion height and regular height, and it's pretty small deformation because it's pretty rigid polymer, but still neck height is actually pretty substantial, and difference in area gives you resolution increase after all this like calculations and measurements 5 times better. 5 times is pretty substantial, because at least this so-called super resolution Nobel Prize was awarded for 4 times increase. Well, that and optical microscopy, which is super popular. So another thing, less scanning artifacts. For example, if you just use regular imaging of adhesion, and that surface might be reflective, you can see well-known interference artifacts. and it can be a kiss of death for any quantitative interpretation of this. So we specifically remove these interference artifacts in ringing mode, because when you do ringing, you can clearly see the zero force. And this is what is needed, and this is what is disturbed when you have needed to remove this artifact, and what is disturbed when you see these interference artifacts. Speed, higher speed. For example, if you increase speed, and again, simultaneously record adhesion, and this is restored adhesion, many channels give you a very toleration up to 20 times increase in speed, while you already have kind of lose of resolution substantially in the other modes. We have some like reason why. If you're interested, I can definitely answer that question. But just this is again like simultaneously recorded. No special adjustments or something like that what was done. Ringing mode can work in liquids. Essentially, we need just only a few oscillations, like 1 or 2 will be already, well, one maybe like 1.5. 2 oscillations after disconnection will be sufficient to extrapolate signal and get this information. This is, for example, restored adhesion on, again, low-density polyethylene, polystyrene in water. This is actually pretty destructive imaging, so that's why you can see erosion starting in low-density polyethylene in water. And this is just a regular P cross QNAM height image for comparison. So a couple of other examples on, for example, fixed human melanoma cells. Adhesion height gives you really interesting features on the surface, which are typically seen in electron microscopy of fixed cells. If you just look at the same time recorded height image, all these features are ironed out. They flattened because of the force pressing down by exposed by AFM probe. Nanoparticles. If you really go to individual nanoparticles, you can really look at, for example, material of nanoparticles, neck height, disconnection distance, coating of nanoparticles, coating with some functional molecules, for example, or just whatever molecules kind of graft into the surface of these particles. And you can compare adhesion, neck height, and disconnection distance, and you can see actually there is there are some correlation, but not necessarily. So all these 3 maps give you different physical information. So now FT-nanoDMA, different universe, viscoelastic properties of materials. How you can measure it? You can do either creep or stress relaxation. That's what's typically implemented in nowadays force microscopy. In this case, what you do, you simply develop some contact and then simply see how this contact relaxes in time. Or you can measure so-called loss and storage modulus, or you can go to much rarely used measurement of creep compliance or stress compliance functions. Without more details, creep stress relaxation are somewhat easier, but they are model dependent. It means that if you want to extract some quantitative information from these measurements, you need to assume some model. Storage and loss modulus is really model independent. The only what you need, if you want really both moduli, you need some contact model to assume, literally to calculate area of contact. If you satisfy with loss tangent, for example, so then it's completely model independent. An area is not there, contact area. Creep compliance is long time to measure and pretty large noise. So it's just literally only a few papers like devoted to that. And this method is like, why to bother? It's like more laborious and it's not giving you good information as other. So we choose storage and loss modulus measurements. And this is what is called dynamical mechanical analysis, or DMA. So why we call this FT? FT stands for Fourier transform. It allows to do measurements of multiple frequencies at the same time. So what is this method in general? Dynamical mechanical analysis is when you develop some contact with the sample, and then you oscillate, well, either sample or probe, and see the response. So you have, for example, in this case, oscillation of your sample with some amplitude, and you measure deflection of the cantilever as a function of time. So today, for example, Bruker's AFM-nanoDMA measures a single frequency in a time. We suggest to measure multiple frequencies in a time because it gives you two advantages. One is more or less obvious increase in time because you process like several frequencies in a time at the same time. But secondly, it allows us to do the measurements so quickly, so we don't need to wait until creep relaxation or stabilization of the contact. That is one of the most time-consuming parts of previously developed nanoindentation. Because in that case, you literally can wait for several tens of seconds, maybe a minute, before you have a relaxation of the surface. In our case, we don't really need for that. We just can monitor change of this area. And like for, I would say, not all reasonable materials, not super soft, we can restrict, and we see that the area of change of area of contact during our measurements is less than 5%. So this is example how we actually then do our measurements. We can use this information, and we extract storage and loss modulus at, for example, in this case, like 10 different frequencies. And this is actually a picture of plant cells from pumpkin. It's a surface of pumpkin seed, essentially. So when you see at each pixel, you have recorded this storage and loss modulus. So 10 and 10, 20, and you have also extract static modulus. So 21 essentially moduli at each pixel. This, for example, is 150 by 150 pixels. So physics of that is fairly straightforward. This is forced harmonic oscillator. And when you crunch the numbers, you get these equations for storage modulus, loss modulus, and tangent delta, or loss tangent. So all these measured quantities directly from the experiment, with the exception of the area. Area of contact has to be calculated from one of contact models. So, and then all these coefficients can be calculated using this either D, which is amplitude of deflection of the cantilever, or Z, amplitude of oscillation of the sample. So what is about this mode? It gives quantitative results. What it means quantitative? Quantitative is really absolute measurements, not relative. How you can know it? First, of course, you compare. You can compare with known materials. Second, it's important that we don't have crosstalk between different frequencies. Because if we don't have that, we work in linear regime, linear stress-strain regime. This linearity is important for all contact and all mechanical models. If you see crosstalk between different frequencies, so you are nonlinear regime. So then your information cannot be trusted. So that's why you have kind of a feedback to understand if your measurements are trustful or not. So this method is, as I said already, the least model dependent. So viscoelastic properties of material, storage loss modulus, and loss tangent can be measured, plus static modulus. So far, we developed pretty much the model, this mode working up to 350 Hertz. It's simply defined by resonance frequency of your scanner. So there is no real serious limitation for that. But for soft materials, it looks like this is the most interesting behavior, because for higher frequencies, you have pretty boring monotonic increase. So if you compare to, I wouldn't say standard, but more classical way to use nano indenters, and compare it to specific state-of-the-art hydrotron. So we have increased up to 150 times for lateral resolution, and similar for vertical. So this improvement is comparable for technological leap from optical microscopy to electron microscopy for soft materials. So I think, yeah, that's really interesting. So increase in speed, even up to higher numbers. And this is really important because instead of really weeks, we can do it really to hours in measurements, which are doable. And it also enables measurements of mechanical properties of many biological materials, for which measurements time is typically limited. And for example, to the best of my knowledge, no other technique can do measurements mapping single cells, and this can. Of course, we do all quantitative analysis because this is important. For example, we did a comparison of our technique with other method. For example, macro-DMA. This is a piece of very homogeneous PDMS elastomer, which was measured with micro-DMA, nano-indenter, and our technique. And actually, our technique is a very good matching macro-DNA, like big macroscopic measurements. With a nano-indenter, we have a fairly good loss, modulus static, but storage modulus sort of like, again, like we have good agreement with macro, but nano-indenter is showing higher. And actually, we have explanation of that because of, again, it's sort of nonlinearity we observe. We use Borkovich probe, and you need to develop pretty large area of contact before you get a linear regime. So then, of course, you go for, again, the static modulus, and you measure this static and loss modulus sequentially, and our 10 frequencies simultaneously. Sequential and simultaneously, and we see the perfect match. Again, this is like loss in air. This is for reference, is static modulus. And in water. So technically, nobody prohibits you to add whatever liquid you want as soon as it's transparent and use optics to detect the placement of cantilever. It works fine. Amplitude independence. The equations I showed you before can be analytically solved if you have, and only if you have this assumption that amplitude of your oscillations is smaller than the initial indentation. So that's why it's important really to see that we don't really have dependence on the amplitude. So, and in air, we can go even amplitudes like up to 20 nanometers. Here in water, it's better to be stopped like in 15 nanometers. Of course, like in water, you have more coupling with the surface. So particularly this would be a problem if you go to very high frequency. But again, like noise is smaller in water or in liquid, so you can really decrease the amplitude in that case. Resolution. As I said, we already have like pretty good improvement in resolution. Technically, if we do theoretical analysis, we should be able to get down to as small as 10 nanometers for polymers. And here we see like either 50 nanometers for polymers and 70 for corneocyte. We actually couldn't find finer structure on polymers or biological surfaces. So this is what we found, and we clearly see that we do resolve these mechanical properties on corneocytes and low-density polyethylene. Time dependence. This is where we change time. It's kind of really noisy, but what happens here, there are 3 different frequencies, and to avoid memory on recurrent of polymers, each point here is measured at a different location. That's why it's so noisy. What happens at this moment, we sharply change the temperature of the liquid. We added ethanol. When you mix ethanol with water, it increases its temperature up to 15 degrees Celsius, and then it cools down back. So you see it gets softer, and then gets slowly again back, and just definitely oscillates because you have definitely convection and so on. So loss modulus is a bit noisy in this case, because this is pretty small anyway compared to the storage modulus. And so technically, if this is a problem, it is possible to improve it even further. But that is again, like, technically there is no averaging here. It's literally raw measurements. If you do averaging, so you can clearly see a change of starting from this like the softest part. This is going through 0.7 second. So it's pretty fast, like scanning can see change of mechanical properties. So after averaging of loss modulus, you have like, well, I mean, there's something different behavior, but at least like it is definitely there. So you can look at and get this picture I already showed you in the beginning, this picture here. So we can look at individual cells. Specifically here, the images were taken on living sprout. Actually, there is sprout here developed. It's a pumpkin seed, which was collected after Halloween. So we had quite a lot of pumpkins around, and we simply planted one seed in petri dish and put water, and it started growing. And then we simply look at different surface area, and we see clearly the structure of cells and different moduli recorded in it. What is interesting, because you record simultaneously exactly the same position, exactly the same conditions, you can not only record this moduli, but you also can look at the gradient with respect to frequency, like how this moduli change with frequency. Again, because it's important you have exactly the same conditions, exactly the same point. And for example, when you literally just simply subtract one image from the other, you can see very clearly some sort of directionality. And when we look at this directionality, we found that it's always like toward the sprout. It's almost like, interestingly, that even on the surface, we have some nutritions going towards the sprout, almost like a sprout is sucking out from everywhere. And it's like, again, not completely clear like why and what exactly it means, but maybe it correlates with some germinality of how good germination of this seeds can be. So it was just, again, for demonstration. Recently, we looked at low-density polyethylene, found different phases, and we haven't really published it as yet. We just literally want to correlate it with some other techniques like Raman, and we do see that we can clearly see three phases, like crystalline, amorphous, and semi-crystalline or anisotropic phase. So you can see that this is the height, this is static modulus, storage modulus in different frequencies, dynamic indentation. Actually, we have simultaneously recorded way more than 21 maps simultaneously, because we can literally, for example, dynamic indentation, amplitude, for what is like cantilever amplitude also, which actually gives you some interesting information, though it is not like physical independent information. You can go for cells, and these cells can be fixed. Why it's good? Definitely fixed cells give you higher resolution. Is it better? There are works showing you that if you do a different amount of fixation, different time of fixation, you still have, for kind of gentle fixation, you have a lot of mechanical information preserved. This is an image of a cell. This is one of the HeLa cells. And you can see this optical image, literally not specifically labeled with this fluorescent molecule. And exactly this area shown here, imaged with AFM. And you can see that optical images not really correlates with this storage modulus distribution. So we have something which is definitely like absolutely new. So it is definitely one of the directions we're trying to understand what exactly we are actually seeing here. And the loss modulus is changing dramatically, and in particular, this is like a log scale. And you also like see some kind of bumps and some protrusions which are not seen in the optical image. So when you have 25 maps, it's always a question how you present it. So you can use that multiple presentation of who knows what. This is equipotential surface, or this is like 3D semi-transparent cube, and so on. This is, by the way, angle of loss, phase. And you also can see like clearly the nucleus here. And again, like multiple things which, like, again, definitely not seen in the optical image. So this is just to give you some flavor. If you want to compare it to existing nano-indenter, it's specifically 950 Hyzotron. They have this nano-DMA. If I'm not mistaken, now it's already a third generation. And this is simply comparing of two polymer samples, PDMS, resin, and polyurethane. And if you want to do the same measurements, how time per single frequency or single measurement compared, just a resolution. Resolution, that's I already quoted that. So it increases more than 100 times, 150 times. In terms of time, just to give you a flavor, so if you want to record 100 by 100 pixel map, which is relatively modest, you need 23 days. It's completely impractical because of thermal drift. You'll get out of the range of your scanner pretty quickly. So from our experiences, like 12 hours, maybe like 20 hours at max, but definitely not that much. With our AFM-based FT-nanoDMA, we have about like 2 hours. And of course, we can get images of individual cells with that high resolution. So far, I'm not aware about any other technique. So there is one European company trying to develop something similar, but they are using more or less like something close to biology, like one measurement per cell or something like that. It's not high resolution mapping. So finally, possible applications. Actually, both ring mode and FT-nanoDMA give you multi-dimensional high-resolution imaging of physical and mechanical properties of materials and surface coating. You can literally go to this multi-dimensional imaging. Of course, the question always like what you do with this wealth of information. You can, of course, combine it using machine learning method, but this may be like additional webinar because we already have done it for medical application and it works perfectly. We can really go to study polymers and composite materials, and we see properties, for example, of nano interface, which is impossible to see by any other means. Imaging of surface coating, it's literally unique ability to see defects in molecular coating down to 1 nanometer resolution. Actually, because of like limited space and time, I didn't really show it to you, and this will probably, I'm not sure we publish it or not, but definitely we can see it in nanoparticles. Surface oxidation, degradation, erosion, definitely. Direct visualization of molecular coating on any surfaces, nanoparticles, polymers, metal, glass, biological materials. Study of cross-correlation between different properties. That's really interesting because you really have simultaneously recorded exactly the same conditions, multiple physical properties. Cross-correlation between them could give you more fundamental information. This is just in the beginning. And the last one, as I said, combination with machine learning or both of these modes can give you really ability to identify surfaces even without getting particular numbers. You literally can use whatever numbers you record, because those are absolute numbers, and to identify some surface, to distinguish between surfaces. For example, we showed recently, well, in this paper, yeah, this one, that we can identify cell phenotype between two fairly simple cancer cell lines of colorectal cancer, which are very close to each other. We can identify each cell line at level of single cell with accuracy of 94%. So it's definitely interesting development for the future. So material processing, material origin, so etc., etc. In the end, I want to, of course, say thank you to my group members, Maxim Dakukin, who is now at NSS, and Renato Aguilera, who is a postdoc in my group, Venkatesh, who did a lot of measurements, Nadia Makarova, she is present PhD student in my group, multiple very talented undergraduate students, collaborators who actually give quite a lot of advice about all the samples we work with. And of course, support with $, it's a National Science Foundation and recently the National Institute of Health. And of course, Nanoscience Solutions, and particularly for this opportunity to present this webinar. So that's it, and I will be glad to hear your questions, if any.
Thank you very much, Professor. We actually got a few questions already, and let me just read it to you and to everyone as well. So, which probes work with ringing mode and FT-nanoDMA?
Yeah, thank you. It's an important question. Pretty much any probe can work with ringing mode as soon as there is some oscillations after disconnection. What we found the best in air and in water, unless you have any special needs, the best is what Bruker called scan assist probes. And by some reason, they work the best. But again, we work with specially made probes, with high-speed probes, and pretty much like everything works fine. With FT-nanoDMA, it's pretty much the same thing. You need, of course, spring constants to match stiffness of your material. And after that, it's important to have not sharp probe. Fortunately, there are multiple companies now making these probes. I think even Nanoscience Solutions also have these probes, which have very well-defined geometry, and it's dull, relatively dull. If it's a sharp, as we showed several publications and people otherwise show that you have non-linearity between stress and strain. And we can see that clearly in cross-talk between different frequencies. But other than that, there is no specific kind of restrictions to the probes needed.
I got another one, and the attendees are interested to know if I have recorded all force curves of peak force scanner. Can I calculate all channels of ringing mode offline later?
Offline, right?
Yeah, offline.
Yeah, that's actually a good question. I heard it several times. The answer is no. Like if you record, first you need a high resolution recording, which would create a gigantic file, but that's okay. But that still would be useless because what we do, we measure the phase. We actually measure exactly the phase shift between motion of the sample and the AFM probe. And this is what, at least to the best of my knowledge, neither of existing sub-resonance tapping modes offer. It's literally like simply kind of put automatically to 0. So that's well, sure, the short answer is no.
Okay. Another question is, are there size limitation on sample for FT-nanoDMA?
No, I think let me show you this picture with, oops. Yeah, you see, this sprout was, and the seed, like it's just a regular pumpkin seed. And it was glued with epoxy to the bottom of a petri dish of a pretty large size. There was no really need for such a big petri dish, but like I think the guys simply used what was available, for kind of the closest what they found. It is a 100-millimeter dish, so it's a little big. So it's we use to control the oscillation. We use endpoint scanner. Endpoint scanner is allowing you, if I'm not mistaken, to put sample up to 100 grams. We don't recommend that because you definitely then you can disturb the oscillation frequency, resonance frequency of this cantilever that way if you put too much. So technically, again, if you have a bigger sample, you can even put it even 100 grams. The only thing you would then need to recalibrate that scanner for that particular amplitude, or sorry, for that particular weight. But if you do like up to maybe like 10 grams, lateral resolution is pretty much, it doesn't matter. So it's perfectly okay. Thickness-wise, there is no limitation. You literally can get like, well, whatever. These measurements were done, by the way, using a Bruker's Icon machine. So it's like whatever clearance you have above, which could be like probably an inch, you can do this with such big samples. Mm-hmm.
All right, we've got more questions. The question is, can FT-nanoDMA work with samples in liquids and in variable temperature?
Oh yeah, that's like what I showed. In liquids, well, this sprout was in liquid growing, and also when we change, oops, it was before. Yeah, when we change temperature, that sample is a piece of polymer approximately like about an inch in size and thickness about maybe like 2-3 millimeters, completely covered with water, and then we added ethanol. So technically, there is no, with these frequencies up to 350 hertz, in water there is no visible, just very slow amplitude. There is no visible limitations. If you put high viscosity oil, yeah, then you would need again to do simply recalibration on some rigid surfaces, which simply would be a kind of a baseline. But even that, it's the short answer is yes. I mean, just we can work in liquids and variable temperatures, no problem. With variable temperatures, again, you can simply like either do it by heating liquids. It will be probably a little bit better. We didn't really try to heat it from the bottom. It really depends on the type of microscope, because in principle this can be installed to any microscope. But it depends, like you need a second scanner. And if you have your own scanner, second scanner, because some of the instruments these days, like latest versions, they have already 2 scanners, or at least an option. So that's some of them already have heating bath or heating plate. So that's definitely can be used. So it's literally, there is no limitation. It's just a regular heating plate can work as well. Mm-hmm.
Thank you. Another question. How unit mode can measure the length of the molecules attached to a sample if these molecules are collapsed in air?
Okay, that's another good question. Because, yeah, on one hand, you have molecules which are really attached to the surface, and when everything is dried, these molecules literally collapse and stick to the surface. And what we found, unless you have really zero humidity, well, even then, surprisingly, at least we have some absorption. Actually, people who work in high vacuum know that it's very hard to degas surfaces or to remove this adsorbed layer. In regular humidity, we have approximately up to maybe sometime on soft surfaces, up to like 5 to 6 nanometers of a layer, which seems to be simply literally like adsorbed water. And so we have, it means that we have surface of our samples hydrated at the nanoscale. So when a probe then touches the surface, you have non-specific adhesion, mostly because of van der Waals, because, I mean, this is universal force. And then when you pull it off, it's not really completely dried layer, which stick and kind of like a crust. No, it is still a relatively mobile and hydrated layer. So we really pull off, and we can clearly see those molecules. That's our explanation, because we clearly see, not of course individual molecules, we rarely see them clearly in the force curves, but as an indication or through energy losses that's projected. Remember that when I showed this explanation of in the beginning of ringing mode was this first, here when we do projection in the past, we never get exactly at the same adhesion. Well, and that means only one thing, there is energy loss. But we can really compare this energy loss to the size of the neck, because we know how much the neck is pulled, because we know all this weight adhesion, because here we have the pull energy neck pulled. So we can really compare and see this is a loss due to molecules, or at least something, because we see mechanical signature. This is not, of course, molecules. It's something which is very, very weaker than interaction with the neck. So, of course, it is our assumption that this is a bunch of molecules, because what else it can be? We can easily measure sorption layer without any molecules. When you do calibration on sapphire, for example, you can clearly see that. That's actually one of things which I didn't really put here. It's pretty quantitative. We can measure amount of energy losses on very clean surfaces, and we have already that quantified. We have to really publish it, but it's there. So it's pretty accurate calculation. So it's, I would say that with certainty of 99%, we are speaking about molecules when we measure these energy losses. Mm-hmm.
Right, another question. To what extent a ringing mode is dependent on the probe size? Is it possible to obtain large resolution images with spherical probes, diameter of CA 5 microns?
That's a good question, because technically some channels, for example, height at 0 force, probably will not give you a huge difference. But if you go to adhesion height, it also always a question if what is the difference between between the area during disconnection and versus area of contact. If you have a big probe, it's probably not super ideal. There is kind of really small roughness there, and it may disconnect at different points all the time. It would be very easy to check indeed, because if you have that probe, you literally tap exactly the same point again and again. And you'll see if it's really repeatable, because there are a lot of stochastics here. Even if you do exactly the same thing, it's like uncontrollable, or I would say quantum, but at least definitely stochastic. And we unlikely can really get exactly the same measurements. I would say we definitely will see something, but the question is, it's better to check than to hypothesize what exactly we would see. And definitely it will be much sharper resolution than just a regular direct contact. Mm-hmm.
Okay, another question. Why ringing mode is faster than other subresonance tappings?
That's a good question, but unfortunately it requires pretty long answer. Probably the easiest one, if we have two versions of ringing mode, and one is it's literally add on to already existing subresonance tapping. And there we have feedback what we already have. We don't really modify the feedback. In that case, it's simply because we don't need to average our data. For example, average to get 1 pixel, you need at least average at least two taps, because the feedback works on the maximum or load force, peak force. First time you have whatever you get measured, but you need to correct feedback, so next will be correct one. So minimum 2. But again, feedback doesn't work like instantly and so on. It's like better 3 or 4 and so on. That's why it slows down. In our method, we really do not really need. We actually can look at each individual top, and each top is actually very weakly depend on the actual force. For example, because adhesion is actually it is dependent on force, but pretty weakly. It's simply viscoelastic or time-dependent kind of second-order effect. If you have a completely elastic material, it should not even depend on the load force. By the way, also like answering maybe like previous question, I'm not fully answered, like how it depends on the radius. For example, again, if you at classical or relatively slow imaging, so then adhesion will be proportional to radius. So in terms of band adhesion, so you definitely will see the difference. In terms of resolution, that's a really interesting question. So it's really, there is no pure answer. So super sharp probes are not needed for that. That's for sure. But anyway, so that's. Oh yeah, and the second, I said like we have 2 versions. Second version, if you have don't have peak force QNM, and we just got this patent. I'm not sure like if NSS already licensed it. I think yes. Another patent on a different feedback, in which we actually develop feedback for each single touch. So we don't really go for peak force as a topic. We just correct the feedback during a single touch. So that definitely like accelerates imaging quite a lot. But that's implemented only for standalone Kringen mode. I'm not sure if you have it already commercially available.
So if you have a few minutes, and probably last question, and I guess I will be able to answer it on my own without asking you and plugging with this. On what AFMs these modes can be installed? The modes can be installed on any AFM, including the old ones which do not have sub-resonance mode. I guess if we don't have any questions, let's see. I guess this is it. Like for those who want actually to get more questions asked and answered, please write us to info at nanosciencesolutions.com, and you will get all the answers in the world you need. Thank you very much.
If you have more fundamental questions not related to particular implementation or commercial availability, always please feel free anytime to ask me. So I'll be glad to. If you have any ideas about collaboration, also like will be great. So if you have any samples to try, yeah, we'll be glad to do that.
Thank you very much, everybody, for
the webinar.
Bye bye.
Bye bye.
You too. Bye.